In this video, we're going to take a look at another example of a linked list problem, which is to merge two sorted lists. So the idea here is that we have two different lists that are in sorted order. So say I have list number 1, and say I have list number 2. And my goal is to merge these into one single list that would be sorted. So in this example here, the list would look something like this, right? We would just have all the elements between the two lists, and it would be in a sorted order. The question is, how can we do this in the most efficient possible way? Well, the idea here is basically that we're going to iterate through both of these lists at the same time. And in each iteration, we're going to pick one of the elements from the list to place in our new sorted list. The element that we pick is going to be the next one in sorted order. So, for instance, when we start this iteration, we have 1 and 2 as options. To have the list in sorted order, we would pick 1. We would then move on, right? So then we could take a look and we could say 3 and 2. Well, 2 would be the next one, so then we move on. So then we have 3 and 4. We pick the smallest one, we move on, right? And we continue along this process until we have reached through all of the elements inside of the lists. Now, there comes a point possibly where we may have iterated one whole list and not completed the other, right? So suppose that these lists were smaller, right? For instance, in this case here, we would have 1, we would then place 2, we would then place 3, we would then place 4. We've iterated all of this list, and only this list remains. What we do is we say, well, the rest of this list just goes on at the end. So we just tack on the 5 at the end. If there were more elements in this top list, like if it went then 7 and then 9, we would just tack on all of these because we know that they must be in sorted order. They're the only elements left, so they're the ones that must go next in the sequence. So that's the general process of what we're going to be looking at for this merge. Let's take a look at how we implement this. We're going to use a similar sort of process as we did with our reversal, where we're going to have the front of list 1 and the front of list 2. And what we're doing is we're going to create a new node, and that node is going to represent our sorted list. It's going to start off with no value. It's going to start off with no pointer to next. And I'm basically going to iterate using it. I'm going to call it the new list front, and I'm going to set it equal to holder. Okay, so at this point, we're going to iterate through our two lists that we have. So basically what we could do here is we could just say, well, L1 and L2. And what we'll check to see is we'll check to see if L1.value is greater than L2.value. Well, then new list front.next would be equal to L2. And then what we do is we just move L2 to its next value, right? So we place that node, we move it to the next value in the sequence. The else for this follows the same sort of process, right? The dot next is going to be equal to L1. L1 equals L1.next. So you see we're basically just picking the proper value to go onto our new list. Then we move forward in the sequence for the next value. Now in each iteration, what we're also going to do is we're going to do new list front equals new list front.next. The reason for this is that we just placed a value on the new list. We then want to move forward to the next slot in that list to place our next value. So we're just continually moving through that. That's the reason why we're setting things up in this way. Basically, what we can do is the holder is going to be the linked list. So we can return back this holder, right, as a result. This right here, the new list front, is being used to iterate through that new list to place the values where they need to go. So that's why we're setting things up in this way. So that's all we need for the iteration. After that iteration, we just check, is there anything left on L1? And if there is, the new list front.next equals L1. Otherwise, if there's things left on L2, then we do new list front.next equals L2. The reason why I can do just an else here is because one of these will have values left on it only, right? When we get to the end of this iteration, we must have cleared out L1 or L2, or both of them. So if there's something left on L1, it would be the only thing with things left on it. If there's nothing left on L1, then there must be things left on L2, right? Or it's empty, in which case this would just be none, right? So that's the idea of why we're able to do this. Finally, we just return holder.next. The reason for holder.next is that the main holder is just a null node. The thing that's next to it is the start of the list. So that's the way that we're actually retrieving that list value. Okay, so let me show you an example of this to show you how it works. I'm going to create a new linked list, and I'm going to insert to the rear of it the values 1, and we'll do the values 3 and 5, right? So we'll do the same sort of example as what I showed you. So I'll say 1, 3, and 5. And then what I'll do is I'm just going to repeat this with the second linked list. And remember, they're both in sorted order, right? So L2 will also be in sorted order, and its values are going to be 2, 4, and 6, right? And what we'll do is we'll just go ahead and say we're going to set up a sorted version, which I'll call L3, merge to list L1.front, L2.front, so we just pass in the front nodes for each of those lists. And then what I'm going to do is I'm just going to do an L3.print in order to print off that list and show you what the results are. So let's go ahead and run this. So do Python 3, chapter 5, merge.py. And I can see here that I get that this doesn't have any sort of print property. The reason for this is that we return back a node. So we can actually turn that into a linked list just by doing something like this. We could say merged equals linked list, merge.front equals L3. And then what I could do is I could just print out merged. Because right now we just have a node, I can't print the node, but I could print the whole linked list. I could have also just iterated the node in the same way that we do in the linked list, right? So either option is fine, right? And you'll see here the result of this is indeed a sorted linked list. So 1, 2, 3, 4, 5, 6, exactly what we expected to get out of this. So my final question is, what is the time complexity of this code? And this is kind of an interesting question because L1 and L2 might not be the same size, right? So what I would say is that the length of L1 will represent as the value n, and I'm going to represent the length of L2 as the value m, where n and m might not be the same as each other, okay? On this iteration, we either iterate all of the first list, or we iterate all of the second list. Here, there's actually no additional iteration required, right? Because we're just setting the next equal to the value. We're just setting a value, so there's no real memory changes here. So from this point here, there's no further iterations. These are all constant time. So basically, it's either on or om. And basically, in this sort of case, what I would just say is that it's on, where n is the smallest of the lists, right? The smallest list size. The reason why it's the smallest list size is because, remember, this iteration stops the minute something is none. So basically, once we reach the end of one of the lists, we're done. And that will always be the shorter list of the two, right? Of course, we won't reach the longer list end before you reach the shorter list end generally, right? So that's generally the thinking here, that O of n would be the smallest list size. We could also say that it would be the largest list size. I guess when you really look at this sort of process, right, we could have a situation where we just keep doing a next on one of the lists and not the other. So actually, it's probably wrong to say that this is the smallest list size. We'll just say that this is the largest list size because technically in the worst case, we could keep pulling data off of one list, and that list could be the longer one, and we could reach the largest one, at the end, right, before we reach the smallest one. So this is probably the more accurate option. But generally, it's not really too important because it's linear time no matter what. Whether it's n, whether it's m, it's still linear time. So that's generally the process here, is that we have a linear time complexity for merging these two lists together in sorted order. So thanks so much for watching this video. I'll see you in the next one.